load resistance RL, often we want to model our amplifier in the absence of RL. How do we proceed with that? In other words, we want to cut from here, still define this node as VO, but without RL. And we want to look back and present all of that circuit with a neat voltage-dependent source with one block. It is more simplified than what you have over here. This is a distributed AC equivalent circuit. Distributed means every member is showing up here. RB is showing, RPi is showing, beta is showing, RC is showing. But you want to combine all of them into a compact form, comprised of an input impedance, a voltage source, and an output resistance. So here is how to do that. When you look back in this direction, I put the eyeball here. This is taken away. How do we determine the Thevenin resistance? Do you remember the test voltage? Test voltage? Think, you know. Oh. To get the test voltage, I'm going to send in a test voltage and then to see the result. But it won't go that far. Here's the reason. To apply the test voltage, you put that source into 0. Okay. Check here. 0. If that is 0, then IB is 0, right? If IB is 0, IC is 0. Okay? Now put the test voltage. What do you see? Don't you see just RC? That's it, finished. So output impedance of an amplifier is the collector resistance, finished. Output resistance is this guy. Because that is a constant current source. Constant, doesn't change. We are talking about AC means changes. So you put that current source to open circuit because when you ground the input, it goes automatically to 0. And you put the test voltage, it sees the RC. You know, you put 1 volt across that, whatever current is 1 volt divided by RC, so impedance is RC. So here is the equivalent source. RO is RC. This is called output impedance without RL. It's very important. And this is the VO. RL is sitting here waiting. RL. It's just sitting here. It's not joined yet. It's just aparted from RL. But then what will be the voltage gain? How much this voltage will depend on the input. Look at this equation that I wrote about the voltage gain. What would be the voltage gain VO over VG if RL was infinity? Check here, RL infinity is not being there. Infinity. It will be just the RC. So here is the answer. You have a voltage source like a Thevenin plus minus. That value is minus GM multiplied by VG. Multiplied by VG. And I'm sorry, AV, I will write it no load multiplied by VG, which is minus GM times RC, VG. Okay. This is that voltage source, GM RC times VG. So what it is, RL is infinity. Infinity parallel to RC is just RC. So RC GM, that's what you have. RC GM multiplying VG. That's your internal Thevenin source, amplifier presented as a Thevenin source. And that's the node VO. What about the input? This is what you have at the input. You have a resistor hanging there. This node is VG, and that value is R in. So this being put into a block makes equivalent circuit for the entire amplifier. Entire amplifier. Starting from here to here. External to the RL. The rest, if you want to calculate what will be when your RL comes in, you can derive it from here. Very, very easily. Just as a check. What happens if I make a connection here? I bring it back. What will happen to that VO? Again, I just change this question to one step ahead of it. What is the VO in here if you apply a VG over there? Without RL, voltage in there is equal to the Thevenin voltage, always. So if you apply VG in here, it will be VG times GM times RC in here, same thing as at the output. The two will be identical. This is not in yet. So GM, only RC counts. Only RC is counted without RL. But if you bring the RL, what will happen? This node will be GM RC VG. It's here. Minus GM, so VO is equal to minus GM RC VG times. That's the voltage here, internal. When you join, this node becomes VO. So what is the voltage at the VO if this is known to be that much? Voltage divider. You see that? It's a voltage divider. Let me write the voltage divider. It will be RL over RC plus RL, because RO is equal to RC. Now, you see this RC, gentlemen, here? Move it here. You get minus GM VG multiplied by RC, RL, RC plus RL. Do you remember what is this? RC times RL over RC plus RL? This one. It came up to be exactly the same thing. But except it's partitioned, aparted from each other. So we have a no load voltage gain. If I ask you what is the no load voltage gain, and for this model, simply you have to calculate AV no load, which means to convert this into AV, this is AV loaded. This is AV loaded because RL is present in it. It's already included in it. If you want to know what would be AV without the RL, simply put RL equal to infinity, it will be just GMRC, which will come back into this one here. And then you can calculate in case, if a resistor comes in. Very simple. You will do this operation. Build it there and then calculate. Now the reason that I am partitioning, amplifier isolating between two lines, this line and that line. The reason that I am isolating is because this amplifier might feed a second amplifier, you see, which is exactly the same configuration. Input impedance of the second, voltage gain of the second, output resistance of the second, you see, and so on. And I can calculate the overall gain from input all the way to final output if I have 2, 3 cascaded stages. So that is why we are trying to isolate one stage into an input impedance, a voltage source, and output resistance. What comes next as a result of coupling can be computed very, very easily once you create between these two parallel line models. So you have to see what the situation is. If there is no second amplifier and so on, you can go at once, use that gain, loaded gain, which is input to the output. This is the formula. RC parallel RL, which I proved it here. See? This is RC parallel RL. Which is exactly this formula. This is known as the loaded voltage gain. This guy. Let's write it down. So this is called loaded voltage gain. This is AV unloaded. Unloaded. It means excluding, I wrote in here, excluding RF. Any external parameter is kept outside the gain. Model it very simply, very easily, systematically, with one input impedance, one unloaded voltage gain, one output resistance, and then you see what comes next. You have a load there, fine. You put the load over there, jump it, jumper the two together, and then calculate the voltage transfer from here all the way to here. So VG transfers here to GMRC VG, then GMRC VG voltage transfers here by additional voltage divider, RL over RO plus RL times that voltage. You've got to get this, see? So this is done. We talked about the input impedance, power gain, voltage gain, loaded voltage gain, and then we talked about dB power gain and model for the amplifier, only excluding the source, whatever business is there, excluding what will be connected in here, whether it is a load resistor or something else, maybe another amplifier, which the input impedance of that amplifier, the second one coming, will reflect as if it's the load for the first one. And that's called, and what will happen, gentlemen, is called coupling loss. When you couple the amplifier, this loading effect, second upon first, reduces the voltage gain. Don't get the impression if that is a 144, you put build another one, you put it there, you'll get the same 144 when you multiply together. No, they don't. This is 144 on its own, you see? Actually, it is more than 144 on its own, because it would be 4,000 times the plus 240. This is on its own, the load is 240 without the RF. Yeah, if you delete this, GM times 4K will be 240. But when the coupling comes in, it drops to 144. That's the problem, with amplifier, with this amplifier, that you have a high output impedance, 4K is too high, and when you put the loads, boom, it drops. We can't afford that in sound systems, because your load in the sound system is a 4 ohm speaker. It's a killer, will bring voltage gain to nothing, basically. So you need some kind of a final stage when it goes out with a very, very low output impedance. Maybe an output impedance of 0.1. It can be done. An output impedance can be designed to be very, very low. Okay, this is set. Now, let me see how much time I have. 450. Okay, now the business of capacitors. How do we design that capacitors? So remember, jot this down, this model, it's very important. It's a model between the two parallel lines, here and here, excluding RL, and that's the way to calculate it, the equations. And the question is this: what is a sensible value for C1 and the C2 in order to present it in the model by a short circuit. In other words, by calling this as short, you are ignoring the AC voltage drop between these two nodes. So I'm repeating. You have two nodes in here, gentlemen, don't you? One is here, the other one is here, right? Two separate nodes because the two ends of the capacitor. Under what condition you can call AC voltage drop in here? There's a DC voltage drop, you don't care. But AC voltage drop in here, when do you call it negligible? What's the criterion for being negligible? Okay, this is what it is. I'll erase this part. Did you take a picture of this part? Okay. So we can call this finding suitable capacitor values based on F minimum. Application frequency, the minimum you anticipate you will get. For example, you're amplifying voice, the minimum frequency, which is we will need to have amplifications about 80 hertz usually, maybe 60 hertz. That's the minimum for a good bass. And then all the way up that you can hear, 100 kilohertz, 20 kilohertz. You can't hear 100 kilohertz, but something like 19, 20 kilohertz. So you want it to be constant. You want this to be considered as short. All right. Don't care about the 20 kilohertz. Just take care of the low end of the frequency, this guy, F minimum. Now, here is the situation. You have a capacitor here, X sub C equal to 1 upon 2 pi FC, this is the reactance, and then you have a resistor here, R, whatever that resistance is, and you have a source. If X sub C happens to be much, much smaller than R, then VI, VO, then VO is approximately equal to VI under this condition. Within 10% error. And it will get even better if you go past that minimum frequency. So if at 80 hertz, we are satisfied with 10% discrepancy error, at 800 hertz, it will be much, much smaller, maybe 0.1% error. So how do we translate this criterion into a numerical value? The numerical value would be, for the reactance, X of C at F mean, make it equal to 1/10 over 10. 10 times smaller. So this capacitance will be 10 times smaller than that. For example, if this is 2000 ohm, we are going to make this 200 ohm. 200 ohm at 80 hertz. If the frequency goes tenfold up, the 200 ohm will turn into 20 ohm, and this is still 2000. So it gets even smaller and smaller as the frequency goes up. So the only end that you have to take care is this minimum end of the spectrum, the minimum end of the spectrum. So that is our criteria. So X of C at F minimum is 1 over 2 pi F minimum C equal to R over 10. Any R. Therefore, C is equal to 10 over 2 pi F minimum R. That's it. This will be our criterion for for choosing the capacitors. You will look what is the accompanying resistance. This is the accompanying resistance. And how do you know accompanying resistance? Short circuit, the source. What goes in series or parallel? Doesn't matter, series or parallel, with the capacitor. If you short, this end turns to here, R goes parallel. You can also look at it R in series. Just doesn't matter, parallel or series. Okay? So whatever resistance goes parallel or series with the C, that is the resistance under consideration. So C must compete, X sub C is going to compete this guy to be smaller than that by at least 1/10 or even smaller. I said, if you take care of that at the F minimum end to be 1/10, be sure when you go above the F minimum and the higher application of frequency, this will be even more true. It will be even more true. It will be much, much smaller. Okay? So this will be the calculation. Now, how do we relate that to our circuit? Here. At once you can create the formulas. You don't even have to write them down or memorize. Here. This is the capacitor. C1. When C1 looks in this direction, you see it says input impedance RA. In this direction, it's a source, it's a short. That's it. C1, 10 times 2 pi F mean times RE. So it is equal to 10, 2 pi, 80 hertz, because this is our F minimum, 80 hertz, times 2400 hertz. Our in was 2500 ohm, 2500 ohm. There you are, finished, calculate. You will see it's like a few microfarad. Number 2. And now you see the significance of this modeling. Watch. Watch this one. This guy. This is C2. This is where it was sitting. It was bridging the collector, connecting collector to the RF. Okay. Put the input to 0. From this end, when you look back, you see the RC. From that end, when you look back, you see RF. Draw them separately. It will be C2. From this end, you will have RC. From that end, you will have RL to the ground. And here you go, value for C2. 10, 2 pi, F mean times total resistance. Do you see RL and RC are series? Do you see that? Mm-hmm. Very, very clearly here. C is sitting here. See, C2. That is sitting series with this one. So here you are, RC parallel RL. Finished. You formulas. So you can determine the capacity. Stick in the values. 4K here, 6K here, that's already 10K. So I'm guessing that this capacitor C2 will be 4 times smaller than this capacitor C1 because it's a higher resistance over there. Stick it there, calculate. Okay? Now let me my time again because this is the final thing. Having said for how to figure out the capacitors, this is the simplest case. And we need almost all of this calculation for the next CE, which is the practical CE. Here is one final thing. So let me see. Can remove this card, remove this one as well. topic is called output maximum voltage swing. Okay. Here. VCE, remember we have IC from your 2200. This is from the EC 2200. VC over IC. We have established a Q point, 4.5, it's this DC, 4.7, 4.7, it's this voltage, DC voltage. Then we have established 1.5 milliamp in the collector current, 1.5 milliamp. This is the DC, and that's the Q point. Okay. Do you remember that your 2200 started with a DC load line? You had an RC in here, and you had a VCE without the capacitor, without anything. You had a DC load line. This DC load line is a relationship between IC and the VCE to keep the transistor in the active region. It looked like this. DC load line. This corner was VCC over RC, and this corner was VCC. This is the relationship between IC and the VCE without RL. Known as DC load line. Please make this emphasis here. It's called DC load line, no RL. RL doesn't count upon the DC of the circuit. Remember, RL doesn't influence the DC because of the blocking capacitor. Now, what happens in the AC? Change of the output, which I said this output is the same as VCE. Remember, we said VO is the same as VCE. Output and the IC. These are changes. Guess what will happen? You need to use IC-VCE relationship of this model, this small signal model, and check and see what that is. Voltage from here to here, VCE, is equal to, which is the same as VO, is equal to minus IC multiplied by not just RC, but RC parallel with RL. So guess what is the slope in here? Minus 1 upon RC RL. Bottom line is, you see the black line here? What's the slope of that line? Slope is minus 1 upon RC. That's the slope of the DC load line. Guess what is the slope of the AC load line? And don't miss me right here, the AC load line. That's the slope. Do you see that? Slope coming from the model, from this AC small signal model. Simply, it's the voltage across this branch related to the current that is injected to both RC and RL, which is this line, gentlemen. There you are. This is known as the AC load line. So when the signal comes in from the input, from this guy, and you're getting that wonderful amplitude, you must not get into cutoff and saturation under the load. So we are estimating in a smart way limits of the saturation. Saturation current that will happen with RL, and the cutoff voltage that will happen with RL. These two ends. So your signal, when it comes in, your swing on the positive is only to the right, and this is called P. Positive swing, and swing to the left. See what that is. If I swing to the left from here, I cannot make my VCE equal to 0 because I have to satisfy that condition. So the limit for my VCE in here, gentlemen, is draw a don't go region 0.7 volt. So this would be my negative swing, known as N. So I'm going to list it in here. P is the maximum positive swing before cutoff, and we can estimate what that is. Very easy. Can you calculate this base, gentlemen, here, the P, knowing that is your ICQ?
What's the Pythagorean theorem?
Huh? Yeah, this is ICQ, and you know the tangent of that angle because you have the AC load line, and the slope of that AC load line is, slope is minus 1 upon RC parallel RL. It's just the geometry. Tangent of that angle is known, height of that line is known as IC/DC quantity. So we can calculate the P. Here you are, answer for the P, positive swing. P is equal to IC multiplied by RC parallel RL. Finish. This is the positive swing. Then it can go before messing up with the cutoff, because causing cutoff for the transistor. The next one is driving the transistor into saturation. So how much negative I can go at the output. Here, when the signal goes down or up, because this signal goes positive, negative. How much down I can go? That is even easier. Negative swing. N is the distance from here, which is the VCE quiescent. That's your VCEQ, the DC voltage you established in the transistor, less by approximately this chunk, 0.7 of it. So here you are. Your N is equal to VCE quiescent less by approximately 0.7 of a volt. It could be 0.8 of a volt, but I mean, we don't care about that. About 0.7. We are assuming that 0.7 volt, when it gets to 0.7, this voltage instantaneously goes to a 0.7. VBE, even if it is 0.8, already this transistor is on the verge of getting into saturation. See? So we stop at the 0.7. This is before transistor goes into saturation under signal, of course, under signal. That's it. Now you can imagine what is your P and N for our circuit. Very quickly. This was 4.7. That's VC. Minus 0.7, 4 volt. So your negative swing, our N is 4. peak. What is P? P is equal to 1.5 milli multiplied by 4K parallel 6K. How much is that? 1 point. 4 and the 6 is 2.5 kilo ohm. 2.5 or 2.4? 2.4? Yes, 2.4. Yeah. So here it is. 2.4 times 1.5. 3.6. Yeah. This is 3.6. 6 volt peak. MPP is defined maximum peak to peak. Twice of smallest of the two. Because you know when we're swinging, we swing symmetrically, don't we? Right? So it is twice of the smallest. Smallest is the 3.6. Almost the two are close to each other, you know this? So 3.6 times 2, 3.6, approximately 7 volt peak to peak. That's a way to estimate how much your amplifier can handle. You make something, how much it can produce signal before it gets distorted. It clips or saturates or cuts off. And that causes signal aberration, signal distortion. So that's what it is. So this was the simplest amplifier I could get to analyze for you, establish the foundation. Next one, when we come into the class, you already have all the formulas. All right? That will be the legitimate amplifier, which is properly biased. But the same ideas that work on this one will apply equally to that. I will not go into this type of analysis. Remember that? Load line was there.